Have you ever looked at the dashboard in your car, or maybe even your phone case, and wondered how they get those perfect, seamless finishes? Well, today we're diving into a manufacturing process that honestly feels a little bit like magic. It's all about creating a flawless plastic part, completely finished in just a single step. It's called in-mold finishing, and trust me, it's changing how so many things around us are made.
So, what is it exactly? Well, the core idea is just brilliantly simple. The best way to think about it is to imagine baking a cake that pops out of the oven already frosted with all the sprinkles and decorations perfectly in place. That's pretty much in-mold finishing. You're combining the making and the finishing into one single seamless operation, all happening right inside the mold.
I know, it sounds incredible, right? A one-step miracle that saves a ton of time, money, and headaches. But come on, is it really that simple? As we're about to find out, there is a whole world of clever engineering hiding behind that apparent simplicity.
To really get why this is such a revolution, we first have to look at the problem it was designed to fix. So let's take a quick look at the old way of doing things, which, yeah, is a story of separate, really time-consuming and expensive steps.
You see, traditionally, making a finished plastic part was a journey. First, you mold the basic part. Then you have to physically move it somewhere else for finishing. Then you prep the surface, sanding, cleaning, you name it. After that, you can finally apply the paint or coating. And then you have to wait around for it to cure before you can even think about final assembly. Every single one of these steps adds time, labor, and, you guessed it, another chance for a defect to creep in.
All right, so that was the slow lane. Now let's jump over to the express lane and check out the promise of in-mold finishing, doing it all in one single integrated process.
Just look at this. The difference is absolutely stunning. You place a decorative or functional film right into the mold, you inject the plastic, and boom, out pops a fully finished part. We've just jumped from 5, 6, maybe more complex stages all the way down to 2. I mean, that's not just an improvement. It's a complete game changer in how you think about manufacturing.
And the benefits here, they go way beyond just being faster. I mean, sure, you shorten your development cycles and slash labor costs, which is massive, but you also cut way down on waste and emissions because you're getting rid of all those secondary processes like painting. And here's the really cool part. The final product isn't just made faster, it's often better. We're talking higher surface quality and even brand new features like scratch resistance that are literally baked right in.
And if you want to understand the kind of quality we're talking about, check this out. For super precise optical parts, think about the tiny complex lenses in our cameras. IMF can get a 97% replication rate of microscopic surface patterns. What that means for you and me is sharper, clearer images, all because the process is so incredibly faithful to the design. That is a level of precision that's just wild.
And that precision has a direct, measurable impact on performance. We're seeing optical parts made with this process that are 2.3 times brighter than parts made with older methods. Let that sink in for a second. That's not some tiny incremental improvement. It's a massive leap forward that can lead to better screens, more sensitive cameras, a real competitive advantage in high-end electronics.
Okay, so it's fast, it's precise, and it delivers amazing quality. So the big question is, why isn't everything made this way? Well, this is where we pull back the curtain and take a hard look at the hidden complexities, the really tough engineering challenges behind all that magic.
As you can see, the list of hurdles is pretty serious. First off, the molds themselves are incredibly complex and, you guessed it, super expensive to design and build. Then, you've got to make sure your materials, the film and the plastic, are perfectly compatible. If they aren't, they just won't bond right. And on top of all that, you're in a constant fight against process defects, like the film wrinkling or air getting trapped. It is a very high-stakes balancing act.
Let's just focus on that tooling cost for a second, because it's a huge factor. With traditional methods, your tools are simpler and cheaper to get started with, but they end up costing you more in the long run because of all that labor and extra processing. IMF tooling is the complete opposite. You have this massive upfront investment, but if you're producing parts in high volume, the cost per part drops like a rock.
But if you ask an engineer what really keeps them up at night, they'll almost always tell you one thing: managing the heat. That little film you place in the mold, it acts like a tiny insulating blanket on one side of the part. This creates an uneven temperature profile, and that can cause the final product to warp or twist. It's a massive, massive challenge for quality control.
But here's the good news. Despite all those challenges, engineers have gotten really good at taming this technology for some pretty amazing applications. So let's move on and see where IMF is already out there in the wild, changing the world around us right now.
You really don't have to look much further than the car you drive. You know those sleek, high-gloss panels on the dashboard, or that durable, decorative trim? A lot of that is now made using IMF. It's how they get that flawless look and tough finish without having to go through a whole separate painting process.
Chances are this technology is in your hand right this second. The seamless, beautiful housings on modern smartphones, and maybe even more importantly, those tiny, high-performance optical lenses inside for the camera, they are very often produced using these advanced in-mold techniques.
And the applications get even more critical than that. In hospitals, medical devices demand sterile, perfectly smooth surfaces that are super easy to clean. By creating a single integrated part with no seams or gaps for germs to hide in, IMF drastically reduces the risk of contamination. It's even being used for really cutting-edge stuff, like dissolving microneedles.
So how in the world are engineers actually overcoming those huge challenges we talked about, like parts warping from heat and those sky-high tooling costs? Well, let's jump into our final section and see how they're actively taming this incredibly powerful technology.
Okay, this is where it starts to sound like science fiction. To solve that heat problem, engineers are now using incredibly targeted heating and these advanced cooling channels that literally snake all through the mold to keep the temperature perfect. They're embedding smart sensors that feed data to machine learning algorithms to control the process in real time. Even the molds themselves are getting a massive high-tech upgrade with things like 3D printing.
And that brings us to a really powerful idea. Additive manufacturing, what most of us call 3D printing, is a huge enabler for IMF. It's letting companies design and build these insanely complex molds way faster and cheaper than ever before. This is blowing the doors open for rapid response production, like making critical medical parts on demand during an emergency. It's incredible.
So if there's one big takeaway, it's this. The barriers to this amazing one-step process are coming down, and they're coming down fast. The tech is getting smarter, more precise, and more affordable every single year. And that leaves us with one final, pretty exciting question. As all these technologies mature and start working together, what part of our world is going to be finished in the mold next?